All right, we're on week 3. We're going to go over a little bit of more things on linear relations. Remember, a linear relation is any relation or function between two variables that maintains a constant rate of change. Now, the important thing here is that it's a rate of change. It's not that every single change is the exact same. It's that the rate is always the same. So I'm going to use some really some simple ones to look at it. And instead of calling these actually x and y, let's say we'll just make up a story that we're downtown and we're walking a few blocks. And we want to know how many minutes it's taking us. So we have blocks and minutes. And we know that after we've walked 1 block, it was 3 minutes that it took us. And after 2 blocks, that took us 6 minutes. And 3 blocks took us 9 minutes. And we forgot to check after 4, but we went to 5 blocks. And so in the end, that actually took us 15 minutes. Okay, now again, you can see we're always changing by adding 3 here up until this point. All of a sudden, we added 6. Now, we can't just say, oh, because this was adding 6, it's not linear. Well, no, it is actually linear because it maintains a constant rate of change. Okay, our rate is always that for however many blocks it is, you're just multiplying by 3 to get how many minutes it took you. So 1 times 3, 3. 2 times 3, 6. 3 times 3, 9. So we can almost say that our rate in this case is 1 block per 3 minutes. Right? It's the same as saying 5 blocks per 15 minutes. Okay? Now even if there was a little extra constant in the back here, so just add 1 to everything, the change is what's important. Okay? Let's say we did add 1 to each of these and say that it took us 4 minutes, or 7 minutes, or 10 minutes, or 16 minutes. Okay, it's again always the change. From 4 to 7 is 3, and that takes 1 minute. From 7 to 10 is 3, and that takes 1 minute. From 10 to 16 is 6, and that takes 2 minutes. So 1 minute for 3 blocks, 1 minute for 3 blocks, 2 minutes for 6 blocks. That maintains a 1-3 ratio. 1 block, 3 minutes. Or I guess you can write it as 3 blocks per 1 minute. Either way. But so again, linear relations, you can see how there's the x input, the y output, 2 variables included, maintains a constant rate of change. When we are looking at linear relations, there are a couple forms we can look at when we're talking about our equations. So there are a few different forms like slope-intercept form, standard form, point-slope form, or even an unconventional one. We'll go over that in just a little bit. Now, I'm sure you're fairly familiar with most of these, but we're going to go over how these kind of fit into our functions. So again, a slope-intercept form, the formula is y equals mx plus b. We've talked about this a little already. M is your slope. That is your constant rate of change that we were talking about before. B is your y-intercept. On the graph, this is where the line will cross the y-axis. Now, how might you see this kind of in a real-life situation? How can you make sense of this? So our example for this would be if pizzas start at $10 and extra toppings on there are 75 cents per piece, we would just say then that y equals 0.75x plus 10. Here's $10, that's what we started at, 75 cents per extra topping. Now we can find the total cost. How does this look as a function then? How would we make a function for this linear relation? We would call our function c, it is the cost. And we want our cost as a function of the number of toppings, t. So we would say c of t. Remember, this is our function notation. You pronounce this c of t equals 0.75t plus 10. So notice, on this side, we have our function notation, function c, as a function of our input t. On this side, we can see exactly the rule, what's happening to t. You do 0.75 times t plus 10 to figure out your cost. So again, this is a pretty easy, the slope-intercept form is probably the easiest way or the best way to think of our linear relations or our linear functions. The standard form of a linear relation, you have to write it in the form ax plus by equals c. Now there are a few extra rules. We normally say that a must be positive, and then a, b, and c must all be integers. So b and c can be negative, but none of these should have decimals or fractions with them. So this would be our standard form. What are all the pieces? Just like this had slope and a y-intercept. Well, a is, you can kind of think of it as the rate of x. B you can kind of think of as the rate of y, and C you can think of as a constant. Now we don't normally see things in this standard form. It's not always as useful, except for sometimes, again, like in a story problem or something, it might be given. Our linear relation might make sense in a standard form, and then to use it and manipulate it, you might want to come back to this slope-intercept form. This is easier to use. This might be easier to make sometimes. So again, looking at an example, if chips cost $3 and pop costs $2, and I only have $24 to spend, and I'm trying to figure out, well, how many chips or how many pops can I buy? Well, I would say it's 3 times the number of pops plus 3 times the number of chips plus 2 times the number of pops must come out to exactly 24. So again, it might look something like this, where ax plus by equals c. So again, in a situation like this, it might be easiest to write it in standard form. If you want to solve for your y, though, and say, how much pop can I buy if I know that I've bought 7 chips or something like that, it might be easier to put it back into this form if you're trying to graph it or do other things with it. If you want to make it a function, though, it's almost impossible to make a function from something like this. You first have to use your properties of algebra to kind of remix this thing and get the y alone. Once you can get the y variable all alone, as in it's the only thing on its side, there's no extra constants, there's no coefficients, once this y is completely alone, then you can call it a function. But then again, once this y is alone, you're basically looking at a slope-intercept form. So again, the slope-intercept form is probably the easiest way to think about functions. Point-slope form is another kind of linear relation that we might be looking at. Another equation for it. It would look like y minus y1 equals m times this whole amount, x minus x1. So again, the pieces of that, there's a point at x1, y1. So whatever a given point there is, you use its coordinates, the x and the y, to say I have x1 and y1. And then as well, this m is slope, kind of like our slope-intercept form. All of these pieces, again, just kind of find their way here. This y and this x will always remain as y and x because those are your variables. For example, if I said something like, by day 7, Greg had already sold 32 things, and he was, let's probably say selling, and he sold, or he was selling 5 things every 2 days. So if they give you a rate, 5 things every 2 days, and they give you some random point, by day 7 he sold 32, well, we have a point, we have a slope, or a rate, so now we can fit things in. Y minus the 32, that's how many things he already sold, equals our slope, 5 every 2, so our slope times the amount x minus 7, the kind of first x value we were given, the first day we were on. Okay, so again, given this kind of problem, it might be easier to write it in a point-slope form, and we do also kind of practice or learn about how we can use this. Again, if you see something in this form, you know there's a point, you can plot it right away. You know your slope, you can find other points. So again, we learn how to work with this point-slope form, but again, thinking about functions, it's probably easiest to get it back into this form, the y equals mx plus b. So all you're doing is adding that y sub 1 to both sides to get the y alone. Just move this piece over, and now you've got your function. You just have to call y your function, or replace it with whatever your function is, and x would be your input value. The unconventional ones, there isn't really a set form for them. They will always have a y and an x, and usually will have some sort of constant. They might also have, not variables, coefficients. They might also have coefficients with them. So if you see something like this, like 23 equals 4 times 3x minus 5y, this is technically a linear relation. Okay, some of the big things that show that it is linear and nothing else. Notice there isn't like an x squared or a y squared or a square root of either one. But because this is all still kind of just to the first power, this is a good chance that it's going to be a linear relation. Again, the best way to check it is to manipulate this equation. If you can get it back into this y equals mx plus b, then you can figure out what the graph will look like, and you know for sure it is linear. But again, you got to make sure you're using your properties of algebra correctly. So again, if you wanted to change this, make it into a function, you would want to change it to get the y alone, and then you would replace it with the function of whatever input. Let's talk about parallel and perpendicular lines. So with our linear relations, again, we always have a constant rate of change, and we call that rate of change the slope. So for parallel lines or parallel linear relations, these will make two lines that never intersect. We can think of these as lines with the same exact slope. Perpendicular lines, again, then would be two lines that intersect at exactly 90 degrees or a right angle. These lines will have the opposite reciprocal slope. Okay, now both of these words are very, very important. Again, same, nice and easy, it's the exact same thing. Opposite and reciprocal, kind of similar to each other, but at the same time, these are different from one another. These both mean something very special. So let's look at, I'm going to make a red line here. It's not going to be exact, but we're going to say that this red line is parallel to that blue line. And by that, we mean that they never ever intersect. Okay? These two lines, they never touch each other, so they are parallel. Now I can move this anywhere I want, and if this extended on forever, it still would never touch this line. Okay? So if the original, the blue line, has the equation y equals 2/3 x plus 5. Okay? And again, I just kind of randomly picked that one to be our original. We would know that any parallel line would have the equation y equals 2/3 x plus something. I left this as a b from our slope-intercept form, the y equals mx plus b, because this b means, well, look, I can put this at a b of 0. I can put it at like a b of 2. I can put it at a b of like -3. Wherever it crosses here, well, it really can be anywhere. The only thing that has to be true for these two to be parallel is that this slope and this slope are the exact same. So parallel lines implies or tells us we know for sure that slope is the exact same. A perpendicular line then. So again, I'm going to make a line. Again, it's not exact, but we're going to say that those intersect at 90 degrees. They make a right angle. Again, notice I can slide this kind of anywhere, and it's always going to be perpendicular to this line. However, wherever I put it, its y-intercept is really the biggest thing that changes. When we're thinking of a slope-intercept form, y equals mx plus b, well, your m is always the same for a perpendicular line, right? Because this slope is not changing. It's just this position. See how here it's hitting at a like a 3 or something like that? If I move it, oops, here we go, move it to there, now it's hitting at 0. Move it, now it's hitting somewhere here negative, like -2 or so. It's always that b, that y-intercept, that is changing. Now notice, when I went from this 2/3 to find my new slope, this was positive. This whole thing is now considered negative. That's what this opposite has to do with. Opposite just means switch the signs. So positive became negative. If it was negative up here, this would be positive. Okay, that's really all that's changing. Reciprocal means that we are flipping this fraction. Instead of 2/3, it's 3/2. Now again, if this was a whole number, say this was 5x, you need to think of it as 5/1, then you flip them to call it 1/5. So opposite, change the sign, reciprocal, flip the fraction. Now we're going to go over horizontal lines and vertical lines. A horizontal line would look something like this. I'm going to do a red one. And it's always the equation for it would be y equals something. In this case, looks like I put it at a place, I might call this right here. If we have an x and a y table, my x looks like it's 0, y is about 2. Go over here, my x is about 2, y is 2. Go one more, x is about 3, y is 2. Come way over here, x is about 9, y is still 2. It has not changed. The only connection between all of these points, this relation that we are seeing, is we have all the y values equal to 2. That's the only way you can make a rule that somehow relates this x value to this y value. Now, if you want to think of it as this slope-intercept form, think about how we go from this point to this point. Think about our rise and our run. We are rising 0 to go from here to here. Our rise is 0 there. We're not going up or down. But our run, we're moving over 2 places. So rise over run, 0 over 2. So our m, or our slope, is 0 over 2, which could be simplified to say 0. So if we have y equals 0x plus b, remember that's whatever our y-intercept is, well 0 times anything is 0, and as a constant that can just be neglected. So any form of a horizontal line will just be y equals b, y equals the y-intercept. Okay, so always write your horizontal lines as y equals something. Please don't put in that extra slope. Vertical lines, on the other hand, are kind of just the opposite. They're the other way. So again, I'm going to draw a vertical line here. These will always say x equals something. So I'm going to say in this case I called it x equals 3. So if I have an x and a y table, looks like I have a point here, 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 maybe way down here. This point here would be 3, 0. The one right above it looks like maybe 3, 1. The one above that is maybe 3, 4. One way down here is maybe 3, negative 3. Again, there really is no other rule connecting all of these points other than, notice all of the x values, they're always 3. So if you were going to, again, do what we did last time, talk about our rise and our run, going from this point to this point, we are rising up 1. From 0 to 1, 1. From this point to this point, though, our run is 0. 3 to 3, we don't move any, so it's 0. Any number you pick up here, anything divided by 0, will always, well, it's not going to be anything. Right? You can't do that. If you were to type that into your calculator, it'd give you an error. So we would call this undefined, or you can just put UND dot. So this would be an undefined slope. That's why it cannot really fit this y equals mx plus b form. It has to be x equals 3. So technically, horizontal and vertical lines are actual linear relations, since they do make straight lines. However, we don't use the normal linear forms for their equations. Horizontal lines could be written in a slope-intercept form with a slope of 0, but we always simplify them instead, so it's just y equals whatever number. Horizontal and vertical lines are special case linear relations. Vertical lines are not actual functions, though. So horizontal lines are still functions. Vertical lines are not functions, because they would not pass the vertical line test. Again, if we go back here, these 4 do not pass the vertical line test. So this is not actually a function, whereas these 4 do pass the vertical line test, so this is a function. So, because it does not pass the vertical line test, it is not a function, and that's kind of the reason they don't fit the slope-intercept form. Slope-intercept form, remember like we said before, that kind of fits our function. All horizontal lines have a slope of 0 and are going to be parallel to each other. All vertical lines have an undefined slope and are parallel to each other. Horizontal lines and vertical lines are always going to be perpendicular to each other. So if I had x equals 3, you would say, well, that is a vertical line. If I said I wanted something that is perpendicular to it, you would say y equals something, just some number. That would be the only thing that's perpendicular to it. And I think that'll pretty much wrap it up.